Beast Games episode 9 ends with a crazy twist, and I have had multiple people approach me as an economist and say, does this make even sense in economics? Like, they're totally doing something irrational right here. And I thought that was an interesting response because when I was watching it, I knew exactly what was going to happen because of the economics of what was going on in the show. So in this short little video, I just want to go through the economics and how we can apply economics here to understand what's going on. We're going to do actual math. I'm going to draw some things out for you. And then I'm going to use that math to show how MrBeast could have saved over $1 million on this episode. Obviously, this is going to contain spoilers, and I assume that you're still watching because you don't care. So what happens at the end of episode 9? MrBeast, who has been talking about the $5 million grand prize for his show the entire time to make sure people know he's giving away the biggest prize in game show history, he comes down and says,
"The next one of you to touch this coin, we'll be flipping it for $10 million.
You know what? We're going to give you a chance to double the prize. There are 6 finalists, and he offers all of them the chance to flip a coin. If they call the coin correctly, he'll double the prize to $10 million. But if they call the coin incorrectly, that person is eliminated. And some people were confused by this. Just to be clear, this is the prize for everyone. This is everyone gets a shot at $10 million, or this individual gets eliminated. And that's one of the sources of why people thought this was a little irrational. Who in the world would jump on that grenade to save the team?
Whoa!
See what I did?
Yay!
I knew it.
I'm going to be honest, I didn't think anyone would take it.
Now, I think one reason why this sounds a little irrational is because one person is being willing to sacrifice for the team. And I think you need to abstract from this. You can't think of this as taking one for the team. You need to just look at the odds of winning. So let's imagine that this is going to be some random just event that determines who wins the grand prize. You can imagine it like I'm rolling a 6-sided dice where I have if I roll a 1, then I win, and if I roll any other number, I lose, right? So I have a 1 in 6 chance of winning $5 million, or I could get a new dice with the 12 sides on it. I can roll that, and then if I get a 1 with that, I get $10 million. But if I get any other number, I get 0. Is this irrational? I think one reason people think this is irrational is because they're thinking a little bit about the odds or something. Like, let's think about this in terms of the expected payout or the expected winnings that these people are going to get. So I've drawn this out. You can get 0 or you could get $5 million. But again, you're rolling the dice, and so every time that you do that, if we imagine doing it over and over and over again and try and get like, what is the average amount of money you're going to earn based off of that first one? Well, 5 out of 6 times you get nothing. 1 out of 6 times you get $5 million. So if we take this the average over just like an expectation is another way that we say this, then you have 1/6 times 5 million is going to be the average payout you get. That is going to be down here at 333. I'm sorry, like there's so many threes. I'm just gonna put 833,000 right there. That is a 1/6 chance of winning $5 million. And 5/6 chance of winning nothing. On the other hand, I have 11 out of 12 chances of winning nothing, right? That's what adding the coin flip does. It basically doubles the amount of chances I get, but half of them I'm going to get nothing. And so now I have, just one world out of 12 where I get 10 million. So we'll put 1/12 over here. And so that means the average out of all of those worlds is going to be $10 million divided by 12, which happens to be, turns out, exactly $833,000. Your expected payout in both of these is the same. That makes sense because you get twice as much money, but now your probability of winning it has gone down by half. So, I mean, this says that on average, you're going to make the same amount of money. At that point, this is looking pretty rational. Why would someone say that this is irrational? The reason why some people might think this is irrational is because you have probably an intuitive understanding of what economists have realized is the key insight to analyzing risk. And that is that it's not the expected payout that matters as much as it is the expected happiness or expected utility. So to give you an idea, I've redrawn this number line with our $5 million and our $10 million marked, right? Let's imagine that the happiness you get from losing is going to be right there at 0. And then for $5 million, we'll put it at a good spot, I guess. And then for $10 million, we know that the happiness we get has to be at least as much as what we're getting out of $5 million. The question is, how much higher is it than what we get for $5 million? Like, is it in the same line? So if I drew this line out and connected the where I am at $5 million to where I am at $10 million, does it just increase proportionately? So that way, like, every dollar makes me just as happy as the last dollar. Or maybe my happiness is a little bit lower. So let's put it right there. Like, it's still higher than what I get at $5 million. But then as I draw this out, I end up over here. Or maybe my happiness from $10 million is much higher than what I would get if I was just going out linearly. So that way, I don't know how straight I'm going to be able to do this. I mean, that's about it. The line is not perfect for sure. But like, maybe my happiness from $10 million is just so much more. And I think the reason why we think intuitively about this is that, like, for me at least, going from $5 million out to $10 million, like, that is just so hard for me to comprehend that, like, I feel like the difference in happiness can't be that much. Like, yeah, sure, I would be happier to get $10 million than $5 million, but I would be, like, so happy to get $5 million. It's hard for me to notice the difference between this, right? So the question then is, which of these 3 points describes what's going on with the people playing Beast games, and like, which one describes you? The nice thing is that all of these are just a function of X. Generally they could be a straight line, curve like this, or curve like this. It's kind of hard to see that as they've all been meshed together like that, but we can just generally describe that as u of X equals X to the P. And if P is equal to 1, it's going to be this line. I'll make sure I put P equals 1. If P is greater than 1, it's going to be here. And if P is less than 1, it's going to be here. Well, which one of these do we think is happening here? It's pretty easy to calculate this out because we have somebody who chose one bid or one lottery over the other. The way that we calculate this is that instead of doing that, rolling the dice and seeing how much money we get, we roll the dice and see how happy we get in each case, right? So in the world with the $5 million, we know that in 5 out of 6 cases, I get 0 happiness. I'm down there at the bottom corner. But in 1 world out of 6, so I can put 1 world out of 6, I get the utility from $5 million. So that's going to be 1 out of 6 times 5 million to the P. That's going to be, on average, how happy I am in the world where I play the $5 million lottery. On the other hand, in the $10 million lottery, I only have a 1 in 12 chance of winning that. So on average, I'm going to get 1/12 of 10 million to the P. And if I choose the $10 million lottery over the $5 million, if I choose the coin flip, I am telling the world that I actually think I will be happier in this world with the $10 million lottery. Now, it's pretty easy to do the calculations here, and you multiply by 12, divide by 5 million over P, and what you find out is that the condition is that 2 to the P has to be greater than 2, or in other words, P has to be greater than 1. We have to be in this world. We call this in economics risk taking or risk loving. Like this is somebody who loves risks. And that makes sense. This is a game show. You don't really get on a game show unless you love risk. But can we say for sure from the actions on this game that P is greater than 1? And I argue that we can. The way we would figure this out, and the way we do this in real economics, is that we offer somebody a guaranteed payout and say are guaranteed to have this, or you can take a lottery where you have a probability of getting this money versus nothing. And then we look at which one they choose using the guaranteed payout versus this lottery. And then that's how we're able to calculate this P. And throughout this game, MrBeast is just bribing people all the time to leave. There's the end of episode 1 where he offers everybody $100,000 for the chance to leave. And then in at the end of episode 2, beginning of episode 3, there's the opportunity to take $1 million to leave. Now, those, I'll argue, are not great opportunities to do this analysis because there's another choice that's going on there. And that choice is guaranteed payout plus leaving versus like the betrayal that you have to do, right? So in the first case, if I take $100,000, I now have to eliminate other people. And so I'm not just getting utility from the money. I have to weigh whether that cancels out the disutility of betraying a bunch of people and becoming a villain on these videos. Same with the $1 million. You don't leave in that case. You get $1 million, but then you betray everybody and then you have this possibility of getting voted out pretty soon. I mean, there's still like an opportunity to do this because, I mean, it's still a lot of money, but I don't think it's the best because there's a couple of different factors coming in at this place. What I think is actually a really good test of this is what happens in the very first minute of Beast Games when Jimmy offers $1 million to anybody who wants to leave, though they have to share it with everybody. And so this is a guaranteed payout with no other things to take into account. It's just, do you want to take this money or do you want to take the chance at winning $5 million? And people are sitting there. There's 1,000 people on that first episode. And so when you start this game, if this was being determined by pure luck, you had a 1 in 1,000 chance of winning $5 million, or the average person is going to walk away with $5,000. Then you also look at like that guaranteed payout, everybody coming in, and you can watch people go up and you can know exactly how much they're making. So you know what is the expected payout I'm going to get for staying here versus my guaranteed payout. And if you stay, that tells you something about that parameter P. So let's go ahead and calculate it. So the way we set up this problem is that we look at what is the lottery, what are they going to get? They have a 1 in 948 chance of winning $5 million. So their expected happiness is here, 5 million to the P divided by 948. And then their guaranteed happiness is 18,868. If they're in and the 53rd person, the 52 people who got it had like around 19,000, a little over $19,000. And so now that you know you're going to be the 53rd person, you take away that 18,868. And so this is a really straightforward problem to solve. I'm not going to go through all the steps. I'll put them up right here. And there you go. From this exercise, we can calculate that parameter, that risk parameter, P, has to be greater than 1.23. That's what they've revealed by making this choice. And that's consistent with what happened in that episode when somebody grabs the coin. You would grab that coin if your parameter, your risk-taking parameter, was greater than 1, and they have all demonstrated that it's greater than 1. So this is perfectly rational based off of their past actions. But we can take this one step further because this is exactly what's happening in Deal or No Deal. You have this option to pick a briefcase and then you start eliminating briefcases. You start figuring out what your lottery is, your chance of winning a certain amount of money, and there's a banker who's offering you money to stop. And so you can use that to calculate out a risk parameter. And what the banker is doing is trying to figure out the minimum amount of money to get you to end your lottery right there. And so let's do the same thing. What was the minimum amount of money that MrBeast could offer these players that would convince them to take that coin flip? The way we calculate this is we just imagine the same thing, coin flip, 1 in 12 chance of winning whatever the big prize is. We're going to call that big prize X. And then we're going to take the other lottery, which is a 1/6 chance of winning $5 million. And right here I put P, but we already know P. We've calculated out that we know P is 1.23 on both sides. So now we have one equation, one unknown. We can solve this very easily. So from that, we can calculate that MrBeast could have offered them $8,886,110, and they still would have taken the coin flip. That means that Jimmy spent more than $1 million more than he needed to get this epic coin flip moment in his show. And so if anyone's being irrational here, it's MrBeast by overpaying. Of course, MrBeast, loves his, big flashy things, and a $10 million coin flip sounds a lot better than an $8,886,110 coin flip. So maybe he's not being completely irrational. If you enjoy economics like this, please subscribe, and you can even check out my newsletter down in the comments.